Today's video will be on exercise 1b, which is found on page 18 of your textbook, question 4a, 7a, 13, and 17. Let's first start with question 4a. Here is the question for question 4a. Find the cube root of 3375 using prime factorization. So first, the question says use prime factorization. This means that we need to prime factorize 3375 first. And prime factorization is this method. First, we divide it by 3. That would give us 1125. We divide it by 3 again, and that would give us 375. We can divide it by 3 again, and that would give us 125. 125 can be divided by 5 to give us 25. If we divide 25 by 5, that would give us 5. And 5 divided by 5, that would give us 1. Hence, we stop at 1. So 3375, this can be written as 3 to the power of 3 multiplied by 5 to the power of 3. Next, we are supposed to find the cube root of 3375. The cube root of 3375. Since there is the number 3 over here, we would group 3 3's and 3 5's together. So 1, 2, 3, 1, 2, 3. Next, we count the number of groups there are. So this would be equal to 3 to the power of 1 because there is one group of 3 3's, and multiplied by 5 to the power of 1 because there is only one group as well. One group of 3 3's too. 3 5's. So therefore 1 and 1. So this one group refers to this one over here, and this one over here refers to this one over here. There is also another method, method 2. So you can either choose method 1 or method 2. Method 2 is this. You have 3375, and that is equal to 3 to the power of 3 multiplied by 5 to the power of 3. Therefore, the cube root of 3375 would just be equal to 3 to the power of 3 but divided by 3. Divided by 3. And why divide by 3? It's because we have a 3 over here. Okay? And then we have 5 to the power of 3. Let's write that as well. 5 to the power of 3. And that is divided by 3 as well. So this 3 is because you have a cube root. This can then be rewritten as 3 to the power of 1. 1 because 3 divided by 3 is 1. Multiplied by 5 to the power of 1. And therefore, this would give us 15. So 15 is your final answer. Let's now move on to question 7a. So this is question 7a. The prime factorization of the cube root of n is given by 3 squared multiplied by 7. Express n as a product of its prime factors. So first note that prime factorization is used to solve this problem. You also know the cube root of n. Okay, and it's equal to this. So the cube root of n, this is actually the cube root of n. So this symbol over here means cube root. Okay, if there is just the symbol, the sign itself without a number on top, this is considered as the square root. So you know that the cube root of n is equal to 3 square multiplied by 7. So this means that the cube root of n is equal to 3 square multiplied by 7. And you're supposed to find n. What is n equal to? Okay, so note that there is a 3 over here. So n would be equal to 3 to the power of 2 multiplied. 3 to the power of 2 multiplied by 3. And this 3 is from here. We mustn't miss out our 7. 7 is to the power of 1 multiplied by 3 as well. So 1 is because in here it should be 1. So although we don't write it, this part here in the square, this number over here in the square should be equal to 1. So therefore we will have 3 to the power of 6 multiplied by 7 to the power of 3. Note that this question says a product of its prime factors. So what this means is actually index notation. And our answer is in index notation. So this is our final answer. So here is question 13. Let's analyze this question. It says that you are supposed to find the smallest non-zero whole number that can be multiplied by 112 to give either a perfect square or a perfect cube. What this means is basically 112 multiplied by a certain number, let's call it p. This would be a perfect square. So first, we need to find out what 112 is. So first step would be to do prime factorization. Prime factorization. What is prime factorization though? You are actually very familiar with this. So all you need to do is 112 divided by 2. What would that give you? That would be equal to 56. And 52, if you divide by 2 once more, you will get 28. Which can also be divided by 2 to give you 14. And you can divide it by 2 once more to get 7. And 7 can be divided by 7 to give you 1. So 112, this is equal to 2 to the power of 4 multiplied by 7. We can then let a specific variable, so I can let p be the smallest whole number, smallest non-zero whole number that we are trying to find. Basically, this is the answer, p. Okay, so smallest non-zero whole number copied from the question. This is copied from here. Okay, so let p be the smallest non-zero whole number, which, so just continue copying, so which can be multiplied by 112 to give a perfect square. Okay, so what this means is that 112p is a perfect square. And what we are supposed to do is find the value of p. What is p equal to? What is P equal to? You should be able to solve this easily. So we know that 112 that is equal to 2 to the power of 4 multiplied by 7. So 112p, we just need to copy this first, 2 to the power of 4 multiplied by 7. Okay, then we zoom in the indices. Is 4 a multiple of 2? Okay, 4 is a multiple of 2. So we do not need to add anything else to it. What about 7? No, 7 is to the power of 1. Is 1 a multiple of 2? No, it's not. So we actually need to add one more. So 7 to the power of 1. So the only thing that we added, multiplied in addition, is actually this, 7 to the power of 1. So therefore P would be 7 to the power of 1, which is basically just 7. So P is equal to 7. Let's now move on to part 2. For part 2, you're supposed to find the smallest non-zero whole number, which can be multiplied by 112 to give you a perfect cube. So basically we can introduce Q. So let Q be the answer that we're trying to find. So let Q be the smallest non-zero whole number which can be multiplied by 112. Multiplied by 112 to give a perfect cube. So notice that whatever Q is actually is just from the question itself. We are actually just copying this whole portion here to give a perfect cube. Okay, so what this means is 112Q is a perfect cube. Okay, from just now we know that 112 is equal to 2 to the power of 4 multiplied by 7. So 112Q, that would just be 2 to the power of 4 multiplied by 7, and then we multiply by 2 to the power of 2 again, because 4 plus 2, if we add them up together, this will be 6, and 6 is a multiple of 3 because we are talking about perfect cube. And then we have to multiply by 7 to the power of 2, 7 to the power of 2, because this is to the power of 1, this is to the power of 2. So when we add them together, we will have 3. So therefore Q is just equal to 2 to the power of 2 multiplied by 7 to the power of 2, which would give you 196. Next, let's move on to question 17a. In question 17a, you're supposed to explain why 54 multiplied by 6 is a perfect square. So to do so, we would first need to do prime factorization. So 54, we can divide that by 2 to give us 27, which can be divided by 3 to give us 9, which can be divided by 3 to give us 3, which can be divided by 3 again to give us 1. And 6 itself can be divided by 2 to give us 3, which can be divided by 3 to give us 1. So therefore 54 is equal to 2 multiplied by 3 to the power of 3. 6 is equal to 2 multiplied by 3. Therefore 54 multiplied by 6, that would be equal to 2 multiplied by 3, cube multiplied by 2 multiplied by 3. We will then combine the 2's together. This would give us 2 to the power of 2, and combine the 3's together to give us 3 to the power of 3. Note that the question is asking for a perfect square. So what does it mean for a number to be a perfect square? This would mean that the indices of the prime factors are multiples of 2. So one very important word here is indices of the prime factors. Indices. So some of you just say, oh, it's a perfect square because it is a multiple of 2. But because if you just say it's not clear. It's not clear. You need to spell out the word indices. So indices of prime factors. This is the phrase that you must have. Indices of prime factors. This is very, very important. Indices of prime factors. So basically, you need a concluding statement. 54 multiplied by 6 is equal to 2 to the power of 2 multiplied by 3 to the power of 4. And then therefore 54 multiplied by 6 is a perfect square. Because the indices of each prime factor so over here I'm referring to 2 and 4. So let's write that down. 2 and 4 are multiples of 2. There you go. Therefore, 54 multiplied by 6 is a perfect square. Or you can also do this. You can also write, so let me write that here. You can also have this instead. You can state that because 54 is equal to 2 to the power of 2 multiplied by 3 to the power of 4. Therefore, 54 can be rewritten as 2 to the power of 1 multiplied by 3 to the power of 2, this whole thing squared. So the presence of this square here shows that it is a perfect square. So this is similar to how you have 3 square. There's a 2 over here, so this is a perfect square. You have 4 to the power of 2, and there's a 2 over there as well, so this is a perfect square. Yeah, so if you have any number, let's say 81, and you have 2, then this is a perfect square too, because there's a 2 over there. Okay, last question. Question 17 part B. Can a prime number be a perfect square? So the answer is actually no. So most of you got it correct. You wrote no, but then you didn't tell me, you didn't explain why. So you're supposed to explain. So the word, if you have the word explain, it means that you have to be very clear. You have to write in words why do you think it's yes or no. So the answer is actually no. So a prime number is only divisible by 1 and itself. So therefore, or hence, the index of each prime number, or each prime factor, which is 1 and itself, each prime factor, which is itself, because it itself is a prime number, right, is 1. And 1 is not a multiple of 2. So for example, 3 is a prime number. 3 can only be written as 1 multiplied by 3. And then the index of each prime number is actually 1. And 1 is not a prime multiple of 2, right? So same goes for 5. 5 can only be written as 5 to the power of 1. And 1 is not a multiple of 2. Same thing, 7 can only be written as 7 to the power of 1. This is because it is only divisible by 1 in itself. Now it is your turn. Flip to exercise 1B, which is on page 18 of your textbook. Complete these questions. Complete question 7B and question 11. 2 questions only. Do them on foolscap paper and they will be collected for marking.